AIMHI is the name of my research lab. So, as the course, I bring some of the validation tests in the course. Here, you can find our team right here and here. And there are about 50 more like this. Sometimes we actually doesn't have a position, but many tests. Unfortunately, the test results were not available, and I just heard that my submission is still in progress because of some of the issue. I think this challenge is truly exceptional in scale and complexity. Because of that, the platform will get faced with technical challenges to make evaluation. But as a participant, I have great experience during this challenge. I really thank the organizers for their work. Just the overview of the challenge. Just briefly, Unicorn is designed to evaluate multimodal foundation models in vertical way. As you can see in these figures. The background is the traditional paradigm was 3-to-1, but in Unicorn it turns out to much many. That means single model evaluating across diverse tests. Foundation models show promise as general systems, but the critical bottleneck was the lack of comprehensive public benchmarks. It was called benchmarking crisis in the challenge. So, the mission was to provide a unified benchmark. It covers diverse tests, about 20 tests. It aims to address fundamental research questions like can a single foundation model under diverse clinical tests. These figures show the dedicated submission pipeline for the challenge. So here's our approach. You can find the same figure on our poster. On the left side, there are modalities, including CT, MRI, pathology slides, and reports for both pathology and radiology. There are various types like CT or kilometer CT, for example. And next, we have foundation models. So I actually use AIMHI Lab, which will visualize data for CT tests. And for MRI, I use the torus segmentator to extract embeddings. In these two tests, we extract embeddings from the specific level of the order stage, downsample and flattened to 1D vector. For pathology slides, I use punch and pipeline, famous baselines for tiling order and slide order. And for visual tests, I use visual tool and prism for the orders. For the reports, I use BioGPT for biomedical language encoder and Python for general language understanding purpose. As an adapter, I use linear probing or pathology regressor. These are baseline adapters, and I built the custom model called linear observable complete adapter. I made this because especially for this segmentation tests in radiology. You can see other adapters. And here are applications, as you know. There are error detection, classification, or region segmentations like that. So, as you can see, our approach was not building new foundation models. Because training such models requires enormous time, resources, computational cost. So, instead, we experimented with existing foundation models across diverse tasks. Our goal was to evaluate and compare the adaptability downstream tasks. this approach is far from trivial because different models must be tested across multiple tests with careful assessment. So here are some candidate models to be considered for foundation models. You can see some visual or CTFM or error segmentator to consider. But our final choices are already created on this slide. I think the unique feature of this challenge is that they allow participants to design custom adaptation. The limitation, I think, of insisting on adapters for segmented tests was that they compress 3D volumes into 1D embeddings. Often they have lower average curve. Then attempt to reconstruct vector 3D, but this progress, special information is already lost. Also, their designs have multiple comp transpose and comp layers, so I think it can be too complex and not suitable for fusion adaptation. So our approach was to retain partial spatial information without GAP and flattening into embeddings. So we use downsample Fisher maps as specific decoder stage of the as the embedding source. And in the adapter, we rearrange the embeddings especially into 2D coordinates and linear observer directly to the target solution, and then apply few constraint layers. So I think it is much simpler, more efficient, and better aligned with fusion application. Finally, this is the case study CD test with NNU. So I used the NNU to train on real data set. This is universal region segmentation data set, which contains a very large number of diverse lesions. I think you already know. So I extract embeddings from the 16x downsample decoder stage, like here. GAP and reference it into 1D embeddings. I applied it to test CT log nodal classification. We achieved unexpectedly decent adaptation performance in the validation test levels. So our interpretation